Hello, judges. We are Hands-on Tech Silicon Valley, and this is our CubeSat, and this is our design review for the Build a CubeSat challenge. This is us. We're a group of high school students in California passionate about engineering and space systems. I'm Yuji.
I'm Emily.
I'm Kelly.
I'm Gabe. I'm Leo.
Our mission is to support national disaster response by detecting power outages after a disaster. To build our CubeSat, we made these smart requirements. The CubeSat must fit within a 1U standard before launching, um, and once it's in orbit during the mission, it will be fully powered by solar panels. In each orbit, it will receive picture-taking location data from the ground station, and capture the images when passing over the specified location. The CubeSat shall then process the images and extract features. And the CubeSat software will load historical data with the same location to detect the power outage, and it will send power outage detection results to the ground station once it passes over the ground station again.
This is the concept of operations for our mission. Before the satellite goes anywhere near space, we go through the testing and design process, making sure all aspects of the CubeSat are good to go, all subsystems are working, all code is running, and we will use a transport vehicle to launch and insert our CubeSat into our target orbit of 400 kilometers above the Earth's surface. Once we are up there, we check all subsystems, and if it's all good up and running, we will go into our routine operational phase where we send data, blackout data to ground station, and receive task planning information from them every time we pass over ground. And for potential risks and failures, we will proceed to the plan such as subsystems isolation or restarts. And if all fails, we will resort to our error contingency mode and proceed from there. Once our CubeSat has finished its mission, we will go into the decommissioning phase, which also may happen if we fail to resolve the issue through error contingency mode.
This is our CAD model, which shows how we've assembled our CubeSat prototype, including and as well as 2 additional features. We've added 4 solar panels for a total of 5, based on our power budget calculations to support our CubeSat during the mission. The 4 solar panels are foldable such that before launching, it will fit within the 1U standard, but after it is inserted into the orbit, the solar panels will expand. And it also has 2 reaction wheels, which are used to orient the CubeSat when taking pictures so that the camera is facing the Earth. We use 2 reaction wheels so that it can rotate along 2 axes. As once the CubeSat is facing the Earth, we can rotate the image in the image preprocessing phase.
This is a system-level block design. The command and data handling subsystem contains the Raspberry Pi 4 with a 32 gigabyte micro SD card. The subsystem is connected to the ADCS subsystem with a ribbon cable, the imaging subsystem also with a ribbon cable, and connected to the power subsystem with a USB cable. The power subsystem consists of a battery which is powered by the 5 solar panels. The ground station command center is communicated to through Bluetooth from the Raspberry Pi.
CubeSat software architecture contains 2 modules, the CubeSat module and the ground station module. The ground station module contains the communications module and a long-term storage database. When the CubeSat passes over the ground station communications module will send scheduled tasks detailing the location for its next image capture for its next orbit, as well as receive outage alerts from the CubeSat its previous orbit, which will be logged in a database for long-term storage and updating a web server for accessible emergency data. The CubeSat contains a communications, ADCS, image taking, image processing, and outage detection modules, which are all controlled by the CubeSat control system. In each orbit, the CubeSat will monitor the ADCS until it has reached the ground station. It is passing over the ground station, where it will where the CubeSat communications module will receive the task for its next orbit. Then the control system will monitor the ADCS until it has passed over the specified image taking location, where it will invoke the image taking script to capture an image, process the image, and then run the detection algorithm, which compares the new image with historical data saved on a local database. It will then write the new processed data onto the late database, and when the CubeSat passes over the ground station again, the communications module will send the outage alerts down to the ground station. The CubeSat control system also checks for any failures and will resort to contingency plans accordingly.
This is our outage detection flow. The image will be taken when the ADCS determines that the orientation of the CubeSat is correct. This way, with the reaction wheels warping the image will not be necessary. However, the image preprocessing must still include the cropping and rotating of the image based on the IMU and gyro data in order to make sure that the image is a correctly oriented bird's eye view over the selected area. The latitude and longitude of the image's top left and bottom right points will be determined by combining data from the time and orbit and the ADCS data of the CubeSat. Then the pixels of the grayscale version of the image will be split into a grid of 3 × 3 kilometers squared longitude earlier mentioned. In each of these squares, the average brightness of the pixels will be calculated. Then a sliding window is passed over these brightness values and compared with historical data on the CubeSat in order to detect the possibility of an outage. The result of the test will be pushed to the ground station. If the possibility of the outage is high enough, the ground station will push the details of the time, probability, and location of the outage onto a web server, which can then be pulled from by emergency response organizations. In the future, we may consider using a lightweight machine learning model in order to improve accuracy of predictions.
Moving on to mass budgeting. As you can see from our tables, for our frame-related components, the total mass is 196.03 grams, and the total price is $69.19. For our electronic components, total mass is 480.6 grams, total price is $314.28. And taking into consideration of the 25% margin, our total mass, which is 676.63 grams, is well under the maximum mass budget of 1 kilogram. And our total cost is $383.47.
This is the link budget for the communication between our ground station and satellite. We will do these calculations taking into parameters such as our distance, which is 400 kilometers, the time window, which is around 10 minutes, and the frequency in which we will be using an UHF frequency band with the frequency as seen above. Using these the parameters, we are able to calculate the free space path loss and noise power. And using that, we can calculate the system to noise ratio. And we have an uplink SNR of negative 2.02 dB and an downlink SNR of negative 1 to 2.02 dB. Using the SNR, we are able to calculate the Shannon channel capacity for both uplink and downlink in bits per second and seeing how much bits we can transfer per second and formatting it into megabytes by multiplying it by the time frame. We can transfer about 71.5 megabytes uplink per orbit and 8.25 megabytes downlink per orbit. And however, each time we pass the ground station, we won't be transmitting images, but we are transmitting data. And we estimated that with each passing, the ground station will transfer about 400 kilobytes of task planning information to the satellite, which is 150 chunks of 256 by imaging information. And the satellite will transfer about 38 kilobytes of blackout information, which is about 300 chunks of information, 300 chunks of 128 byte blackout data. As you can see, if the numbers were well within the budget.
Moving on to data budgeting, assuming we take 5% of a spherical sector with 400 kilometers, the area of that sector would be around 800,000 square kilometers. And since we're taking 3 by 3 kilometer grids and we store each grid to one row in the database, we need around 5.7 megabytes per pass. And since each orbit takes around 1.5 hours, we need around 16 passes, which totals to around 90 megabytes per day. And since we're using around 10 gigabytes for databases, we can last for around 100 days.
This is the power consumption for our power budget. So each orbit is 1.5 hours, and the battery given has a capacity of 180 kilojoules. So in the table, you can see how much energy the Pi when it's idle and the Pi when it's running uses. So the Pi when it's idle uses 21.438 kilojoules, which is about 6.8% of the battery every orbit. And when it's running, it uses more power. So it uses 26.838 kilojoules per orbit, which is about 10% of the battery. And you can see the more detailed subsystems and how much power they use in the table. And here's the power generation. So we base the solar panel size off of the size of the solar panel that was provided, which is 0.008 meters squared. So this table is assuming that the solar panels are exposed to sunlight for 0.9 hours per orbit. The solar panels have an efficiency of 30%, and the average angle to the sun is 45 degrees. Based on this, we can calculate how much energy it would generate per orbit, which for one solar panel is about 8 kilojoules and about 4.4% of the battery. So based on this, we need four solar panels of the size provided in order for this to work, but 5 would be better for redundancy. So this is our integration and test plan. So the parts and software will first be individually tested to make sure they all work before they're put together. So the solar panels will be tested by placing it under a light source and see if it generates enough power, power at the expected rate. So the light source will probably be the sun, and the IMU, reaction wheels, and the battery will all be tested to make sure they work. And the camera, the image processing systems, and the transmission will all be tested in an environment that simulates a functional CubeSat, like in low Earth orbit. The fully functional or assembled CubeSat will also be tested in a special simulation environment that simulates how it would be like when it's functional. And the error states, like the CubeSat being out of power, will also be tested, like the error contingency systems. So the CubeSat will be forced to enter these error states.
This is the simulation environment for our CubeSat city, the CubeSat mission, which we replicate a night city by strapping down LEDs to a dark plane surface. And we covered some of the areas of the LEDs with dark tape to simulate outages. And we took pictures of both before and after covering the LED sections up and put them through our CubeSat model to simulate as if our CubeSat was taking pictures in space and to assess if our CubeSat can correctly identify which areas are experiencing the said blackout. Through this, we are able to simulate the CubeSat being in orbit and their operational phase in which they take pictures and compare them to historical data. Thank you for listening to our design review.